All right, welcome. So this is the final session that we're going to do on the hands-on machine learning book. So starting last year, we did all of part one, which is like core traditional machine learning. Part two, deep neural networks. We've talked about a couple different architectures, CNNs, which started out for vision, and then RNNs, LSTMs, transformer, which started out for NLP. And we have a variety of topics today to round things out. This is the chapter titled Autoencoders, GANs, and Diffusion Models. And there's a little bit of a connection between these. The core takeaway will be that you may not use these particular designs standalone. So you may not say, oh, I've got this project at work and we need to predict churn. So I'm going to build an autoencoder. I'm going to build a GAN. I'm going to build a diffusion model. But more and more these days, these are building blocks inside of pretty much every large, high performing model that you see. So super important concepts to understand. I'll go through as necessary the different parts of the book. But what I'm hoping to do is to really supplement with like the intuition behind these architectures and not necessarily go through the details of the code or this or that unless people have specific questions. So as usual, I'll just pause before we dive in and just see if there are any particular questions people had, people who looked at the chapter, any questions about the content, exercises, any of that. I'll make notes and make sure to hit those as we go. So just pause for a moment and see if anybody has any particular questions. All right, then we'll just jump in from the top. All right, so the first thing to know about these techniques is at the core, they're unsupervised learning techniques, or maybe you call them self-supervised learning techniques. But the key thing is that they don't require massive amounts of hand-labeled training data. In self-supervised, you're using some type of noising, masking technique in order to give your model a target for what's to learn. But again, it's about not having hand labeled data. So, for example, just to be crystal clear, hand label would be I've got a pile of 1,000 images, and 500 of them I've said these are cats, and 500 I've said these are dogs. Okay, and if you took an image of a dog and you just added some noise to it, then you never had to label it. If you took a dog and you took a crop out of it or two different crops out of it, that would not be something where you had to hand label it. So all of these techniques work well with that type of self-supervised, unsupervised learning. And that's what makes them very scalable. And that's why we see them in these large systems. So the chapter begins with a section titled Efficient Data Representations. And I actually really like the example that they cited, this Chase and Simon research. So this is one that's kind of stuck with me. They showed chessboard positions to chess experts, and what they found is that people who were experts at chess could memorize the position much, much faster than a normal person like me. So they said 5 seconds, and boom, they would have it like perfect. They'd have 99% accuracy, just recalling where all the pieces were on a blank piece of paper. But if you showed them a chessboard with the regular chess pieces just randomly placed on the board in completely unrealistic positions, then they did no better than you or I as a regular person. And so the takeaway from that, right, is that they had certain concepts, certain structures, certain distinctions, certain ideas that would allow them to sort of compress understanding. Like if it's very early in the game, I know a little bit about chess, right? You could say like, well, this is only 5 moves into the game. Almost all the pieces are in their starting positions. And so I just see like blah, 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 blah. A handful of things have moved, right? Obviously there's different ideas for later in the game and whatnot. But so for me, this this really kind of ties in with I don't have an attribution for you, but this idea that compression equals understanding, compression equals intelligence. Okay. They have an example in the book that if you have the series 50, 48, 46, 44, and it's just going down by twos, you can compress that into, well, it's just the even numbers from 50 down to 14. And so you need about 3 pieces of information. I don't know the size of each piece of information, but you need 3 pieces of information. You need to know that it's evens, it's starting at 50, it ends at 14. And then they gave a much shorter list of just random numbers, and it's very hard. So in some of the debates about LLMs, I argue that because the LLMs are able to compress a whole lot of world knowledge, a whole lot of understanding of relationships into, I know that, like, whatever, 700 billion weights is not a tiny thing, but if you think about all of the understanding, all the facts that it has, it's still kind of impressive to me that in 700 billion floating numbers, you can do all of history and physics and math and this and that and that and that, whatever. Now, I'm not saying that that intelligence is similar to our intelligence. I'm not saying that the LLMs unlock it in a way that humans are able to. But I personally would define that as a form of intelligence, just the mere fact that it's able to compress representations of world understanding and to know different kinds of cars, different kinds of planes, different kinds of engines that go in old-fashioned Model T Fords, modern cars, racing cars, jet engines, all that kind of information. So when we talk about an autoencoder, really what we're going to do is we're going to try to compress the information that we have. And if you have useful concepts, then they will allow you to compress a lot more than if you have very unuseful concepts. So if you just said chess pieces, I'm going to think about round pieces and pointy pieces and things like that. That might not actually compress the information about the state of a chessboard very well, whereas a more experienced chess player would probably have certain information about, like I don't know, like the king, you rarely ever move that except when you castle. And so that you probably, for most situations, need about 2 bits to understand where the king is. It's an original spot. It castled on the king side most of the time. It might have castled on the queen side occasionally until you get to the very late game. And then there's a completely separate set of distinctions. So things like that. So the book walks through fairly slowly some simple examples, and they start with just this model that has 2 layers. The encoder has just 2 neurons, the decoder has 3, and they say if you pass in 3D data, so like XYZ coordinates of information, that this model will actually compress that down to 2 dimensions. I know, not the most amazing, fantastic thing. But they say if you don't actually use any activation functions, no ReLU, no sigmoid, anything like that, and you just build this, that actually what it's going to calculate is PCA, which we talked earlier about in dimensionality reduction. And you could do this for any other number of dimensions. It's just 3 is easier for us to visualize. So they show some code, and then they have an example where here's a data set of red points. They do not all lie in a plane. It might be a little hard to tell from the diagram. Let me make it a little bigger. That did not seem to work. Little. But ultimately, what we'll get out of the 2D representations in the middle is the PCA projection of these red points onto the best fit plane that's in the middle of them. Okay, and so you can see this diagram on the right looks like if you took this blue plane and ripped it out and just held it up straight like a piece of paper, what the dots would be. And so obviously this is not the full information because some of the red points are above the plane, some of the red points are below the plane, but this is exactly PCA. Okay, so this is a more interpretable way of compressing. Okay, and again, 3 to 2, not the most impressive thing, but the point is that you can actually compress all sorts of things like images and text and whatever other kind of information. All right. So they managed to do this. Yeah, please. I didn't get a chance to test the microphones. We've got a whole pile of them up front, so hopefully the batteries are good.
Thank you. Would you mind scrolling up just a little bit to
Yeah.
see the autoencoder? A little further up.
This guy. Yeah.
Yes. I was wondering if why would you need three outputs if you're going from 3D to 2D? Or is that just like a little example?
Oh, great. Yeah, I went a little too fast, so I didn't explain. So what's going to happen is this first layer is going to go from 3D to 2D. The second layer is going to go back to 3D, and we're going to compare those outputs to our original inputs. Okay. So what autoencoders do is they try to mimic their inputs. And usually what you see in a traditional, we'll talk about some other kinds, but in a traditional autoencoder, we're going to squeeze the middle so that it can't just literally copy the inputs to the outputs. Okay. So if this was 3 and 3, then the simplest thing that it could learn is just the identity function and just pass the input to the output. Okay. But since it's only 2, there is no way for it to literally copy. And in this case, the function that will lower the loss, if we just do like mean squared error between the input XYZ coordinates and the output XYZ coordinates over a large data set. So we saw with the red points, it's like about, I don't know, whatever, 30 data points. If we minimize the mean squared error averaged across all 30 of those data points, then the optimal representation from the first layer with just the 2 nodes will be the 2D PCA embedding.
Got it.
And then, so that's why we say that we have an encoder and a decoder. And when we're looking at those blue dots, it would actually be reading the outputs of the encoder from the middle. Okay. So I apologize. I went pretty fast through there. Didn't really explain that.
Thank you very much.
Yeah. You pass the mic up.
So does that assure that you capture the maximum variance? And that's why you're saying it will be PCA. Does it actually use the algorithm to get that,
The learning will just use gradient descent like we've used for all of our neural networks. So it will not be using formal PCA, which normally we solve with a singular value decomposition.
Correct, yes.
I'm trying to think. So what you can prove with the singular value decomposition is that you're preserving the maximum variance
Correct, yes.
in the remaining data. So this would be the 2D data. Okay.
Yeah.
But how I can say that another way is that I'm minimizing the variance that I've lost in the throwaway dimensions.
Yeah, that should be fair, yeah.
And that's what this model is doing, is it's saying I need to squeeze it to 2, I need to throw away information. It's trying to minimize the amount that it throws away because it's going to do reconstruction. And because it's throwing away information, it will have errors. And by minimizing the amount it throws away, it's the same thing as maximizing the variance preserved, which ends up being equivalent mathematically, getting the exact same numbers you would get if you did PCA.
Sounds.
Yeah. Do you want to add something? Yeah.
Yeah. So one other piece with PCA versus the autoencoders is PCA is linear. So when you start doing stuff with autoencoders and you have all these activation functions and everything, it can mean significantly different things than if you're doing SVD and PCA. You have much more capacity out of these autoencoders than you do with just SVD.
That's exactly right. So that's the perfect segue. So if we had just one layer and no activations, it's linear, it's PCA, but we can add activations. And what we can do is we can have multiple layers. So they show us a stacked autoencoder now with 2 layers, okay, in the encoder and 2 layers in the decoder. And just like Ryan said, we now can do more powerful things. We could do nonlinear things. You can do regular old PCA on MNIST or on images of cats and dogs. It won't be that powerful because it turns out that dogs and cats are not that linearly separable. Okay. But you can build it and it'll work. It'll have whatever accuracy it has. I don't know, 70% accuracy. All right. You can, however, get to 99% accuracy if you build something a little bit more complicated. Right. So here in this chapter, they're using this fashion MNIST data set. So I believe these are 28 by 28 black and white or grayscale images. And so what you do is you take this 28 by 28, which is, what is it, it's like 764 or something, I can't remember. 764 pixels. You pass, oh, it says right here, 784. You pass the 784 pixels into the input layer. It's getting squeezed down to 100, and then it's getting further squeezed down to 30 floating point numbers. Okay, so we're doing a, what is it? Over a 20 times reduction in the amount of information, because we're going from 784 floating point numbers to only 30 floating point numbers. Okay. Then you can see this line here. This is where we, if we wanted to read the codings, this is where the compressed information lives, is the output from this pink layer. The decoder's job is to reverse that process, so to speak, and it outputs the full 784 pixels, which we rearrange in a square instead of just, you know, a flat single vector. And if you train this code here that they show in the book a little bit, then you can take the top images, the top row, these 5 images, and what gets output by the decoder is these bottom images. So really not bad. And again, this is just whatever, 100 plus 30, you know, 130 hidden neurons in order to represent these somewhat diverse looking images. Okay, so showing the power that we can do not just something linear like PCA, but we can do more complex things. And you won't be surprised, the next section, what we're gonna do is we're gonna make it even more complex so that it works a little bit better. Yeah.
Can you comment a little bit on why is there 2 hidden layers? Why go from 784 to 100 and then to 30 as opposed to 784 directly to 30?
Yeah, that's a good question. I think I have an intuition. I don't know if it's 100% theoretically sound or whatever. But in general, in deep learning, the complexity of relationships that you can represent grows sort of exponentially with the number of layers. Okay, so what you can represent with a 2-layer network with 130 is, don't quote me super literally, it's more akin to something that was ballpark 1 to 3,000 nodes in a single layer. Okay, and it's way more complex representations than you could represent with just 130 in a single layer. So you're getting more bang for your buck when you go deeper. Okay, now we could kind of get into it, and so there are going to be some symmetries because you know, the way the 100 interact with the 30, there's only so many ways that they can do it. It's not going to be the same power as if you had a full 3,000 individual neurons. But the main thing is just computationally, you get a lot more bang for your buck. So yes, if we want to do a quick test, we could probably do something that's maybe a little less than 3,000. So maybe, you know, 1,000, 2,000, 2,500, and we would probably get very similar results. And so then you can imagine that as soon as you go to 4 layers, right? If it was 4 layers of 30 each, forget about the different sizes. Then you're talking more like the equivalent of 30 times 30 times 30 times 30, 30 to the 4th power. So whatever the heck that is, you know, 8 million or whatever in a single node. And so you're a lot better off having 120 nodes stacked than paying the compute for 8 million nodes horizontally. I believe also that empirically it learns faster and better when you use deep instead of an 8 million wide thing. So not only you're saving compute, I think it actually just works better. But it's a very good question. I'm not sure if we have the full theory that says exactly why, but this ultimately is the reason why deep learning is the solution for ChatGPT, for, you know, all of these modern deep learning models, because it does work better. All right, so so I went pretty fast, but the key idea here is that we are trying to reconstruct our inputs. Let me check the chat real quick. All right. We're trying to reconstruct our inputs, and in this case, what we're doing is we're squeezing so that it can't just copy. The book does note that if you had data, if you had a large enough encoder, a powerful enough neural network, then even if you squeeze it down, it might figure out a sneaky way in which to represent the information. So for example, I said, well, there's only 30 floats in the middle, but each floating point number has a lot of different values that it could represent. So if you had 1,000 items in your training set, hypothetically, a certain kind of autoencoder could figure out, I'm going to have a 1 in the middle if it's image 1, and I'm going to have a 2 if it's image 2, and I'm going to have a 3 if it's image 3. And the decoder just needs to be powerful enough that says, anytime you give me a 1, I'm going to output this shirt. Anytime you output a 2, I'm going to input this shoe. Okay. So it's not to say that autoencoders don't have any possible failure modes, and that if you just built the big enough one, then you don't need ChatGPT. I'm just going to build this giant autoencoder and you can do everything. Okay. But this is a fundamental technology that, again, is super powerful because you don't need to label the data. So you build a slightly bigger autoencoder, and instead of giving it 1,000 fashion images, you give it celebrity faces, it'll be able to handle. Okay. You build a slightly even bigger one and you give it whatever, all of ImageNet, it'll be able to handle. That's the general pattern here. All right. Moving on, they did this nice thing where they took the fashion MNIST images. They took that 30-dimensional representation that was squeezed in the middle, and then they ran TSNE, one of the dimensionality reduction algorithms that we talked about. I'm probably a broken record. Every time I see TSNE, I say almost reflexively, probably should have used UMAP instead. But nevertheless, you can actually see here, if you look at the different colors representing the 10 different kinds of things. I don't remember what they are, but there's different kinds of blouses, different kinds of pants, different kinds of shoes. That down here, orange, we've got certain pants that have clustered together. And then over here in the light blue, we've got certain kinds of shoes that have clustered together. And so we can do a little bit of interpretability work, and we can say that it's intuitive to us that this 30-dimensional embedding in the middle did in fact have some semantic compression that we would relate to, right? I would agree that sort of the pants that are in the orange are more similar to each other than the shoes that are in the light blue. Okay. A complex system, we can't always interpret what's in those interior embeddings. I can't tell you exactly what's going on inside of ChatGPT, but the idea is that we're squeezing it, and we did not have to handcraft that compression algorithm. We did not have to hand label everything. And so if you have a big enough data set and the right kind of autoencoder, you can just get really good features by shoving stuff in there. All right. So quick comment here. I've been talking about you can get really good encodings from information. Why would you want to do this? Typically what happens is if somebody else can give you a large pre-trained model, then you can do what we've talked about. You can do transfer learning on it. Okay. So it's possible that somebody would build a very large autoencoder, train it on ImageNet, and then basically in the encoder part, the part that's on the bottom, you could take that and you could reuse that portion. So you see here, here's an autoencoder that's been pre-trained. You can copy just the encoder part. And then if you say worked for Toyota and you wanted a model that would recognize the different models of your different cars, okay, rather than training from scratch from random weights, you could take this encoder, which already has feature extraction, good features baked into it, and then you can put a little prediction on here that says this is a Camry, this is a 4Runner, this is a, I don't know what all the car models are, and you can fine tune it on maybe a couple thousand images, whereas this original thing might have been trained on millions and millions of images. So once again, that theme of transfer learning, something we see a whole lot in the real world. There's another section that mentions this idea of tying weights. So if you have a symmetric looking autoencoder where, you know, we see sort of it's a mirror image in the vertical direction, then what you actually can do is you can have the weights for, say, you know, the two blue layers, where the encoder weights are whatever they are, say 100 by 30, and then for hidden 3 you have a weight matrix that's 30 by 100, and it's literally just the transpose of the 100 by 30 matrix used by the encoder. If you do this, you're going to save a whole lot of memory, and your model is actually going to learn certain things faster. Not saying that it'll, in the end, it'll be a better or as good of an autoencoder as if you let them float freely, okay? But it is going to train faster because it's getting that hint in terms of both the encoder, and since the decoder needs to reverse the encoder, right, by it having the same weights, it can do that really fast. And so I thought oh yeah, so you actually will see this pattern not for the entire model, but one place where we still see this today is when people have small LLMs, the very first layer is the embedding layer. So you have a vocabulary of whatever, 50,000 words. You know, word number 1 is the, word number 2 is apple, word number 3 is, I don't know, pencil. And so then, you know, 1 gets converted to a dense vector that's used inside of the model. At the far other end, after it's gone through all the transformer layers, then you have a prediction head that says, hey, what is the probability of these different tokens? We have an unembedding layer, and the unembedding layer takes these dense vectors, and it has to then output likelihood for it being a 1, the word the, likelihood for it being word 2, apple, likelihood for it being word 3. Did I say pencil? In large models, people don't do this, but in some small models, people will actually tie those weights. And so the unembedding matrix will be defined as the transpose of the embedding matrix. And when you train this model, the model will, my understanding is it'll learn a little bit faster. But one of the key things is that in terms of if you're putting this model on your phone, it's going to take less memory because you don't need a copy of the embedding matrix and a copy of the unembedding matrix. You can just have one copy and then just transpose it when you want to use it for unembedding instead of embedding. There's a section about training layer-wise, and I think that was an early technique. It may have some historical significance if you're curious about it, but I haven't seen it. I can't recall actually ever seeing it. So I don't know, Ryan, have you ever seen layer-wise training in the last 5-10 years? Yeah. So I don't think that's a terribly important concept. Okay. So we said you can do 1 layer. Technically, we said 1 layer, no activations. You can add activations. You can have 2 layers. What else can you do? You don't have to use fully connected layers. You can use CNN layers. All right. And so that was a pretty natural extension. It turns out that it can be a little bit finicky trying to do this. But eventually people did build convolutional autoencoders, wasn't too hard. And just in the same way that we saw CNNs are really great for images for things like classification, CNN layers make for great autoencoders. All right. The next kind we have is now taking a slightly different tack. So this is a denoising autoencoder. And in this case, the image that we are inputting into the model is no longer the full raw image. We're actually adding noise to it. And the prediction that we're looking to get was the original image before we added noise. The key thing here is that we said if you had a big enough model and you didn't have a bottleneck in the middle, it could just copy the inputs to the outputs. When you have a denoising scheme, you don't have to worry about this anymore because you aren't showing the model the actual original inputs. You're adding noise to them in some way, masking out parts or literally fuzzing the numbers by adding noise before it goes in. So now you can build as powerful a model as you want. It can be anything you want, and you don't have to worry about it cheating. Okay. So here we see with Fashion MNIST, these are some pretty badly pixelated, noised input images. And I think that this model shown in the book did a pretty decent job of actually guessing, saying, well, if this were from the distribution of Fashion MNIST images that you trained me on, that you showed me, I think this first one is this particular kind of a top. I think this last one is this particular kind of a shoe. So pretty impressive. The takeaway here is denoising autoencoders are cool. And if you actually have something noisy like a fax or a photocopy of a piece of paper, then you can use a denoising autoencoder to clean up, take away some of the speckles and things like that. That's something that people do. But more importantly, this concept of noising or masking the original sample is one that now has been extended over and over and over again. So BERT is a language model. If you guys kind of know your early LLM history, we still use variants of BERT today for things like sentence embeddings. So it might be a slightly different one. It might be a Roberta or Distilbert or something like that. But there's still these BERT-based models. And the way those are trained is you put in a sentence, and in the original BERT model, 15% of the words, you would just mask them out. You would delete them, and the model had to try to predict what were the words that were missing. Okay. So this is denoising autoencoders on a much larger scale now with transformer linkers. If you think about it, and you have to kind of like squint a little bit, okay? But ChatGPT, the way its main training is done, it actually is a denoising autoencoder. We take text, so let's say 4,000 tokens of text, okay? But the noise has a very special pattern. Instead of just deleting 15% of the words at random, okay, we have this auto-regressive mask that says the part of the LLM that's trying to predict the fourth token has all of the fourth through 4,000th tokens deleted. So it can only see the first, second, and third. The part of the model that's trying to predict the 10th token can only see the first 9 tokens. The part that's trying to predict the 3,001st token can only see the first 3,000 tokens. So if you've heard about this auto-regressive mask, it kind of makes sense in terms of if you didn't do this, it could cheat. It would just see the copy of the 10th word and it could just output it at the top. Okay. So it's a little bit different to think about this because you have to think about it specifically from a particular token position. Okay. But from the perspective of the part of the LLM that is predicting the 10th token, it's being noised such that out of those 4,000 tokens, it can only see tokens 1 through 9. And so it really fundamentally is a denoising autoencoder at its heart. Did you want to add?
Yeah, so these are different in different domains. So like they're showing an image one. On Kaggle a long time ago, there was a very famous case of someone who trained a denoising autoencoder for tabular data. So what does that look like for tabular data? What they were trying to handle was in tabular data, very frequently you have missing information of some form. So just natively, your data is already missing something. And so what they trained with their denoising autoencoder was basically saying, train my model to try and reconstruct all of the missing values. And then that became extremely powerful for their model because it was able to kind of impute all of the missing things directly from the data. So it built a really good representation, and it could fill out if they're missing their credit score or whatever for the stuff that they were trying to predict. It can kind of fill in all of those values. So it's different in images or text or everything else, but you can even use it for tabular.
That's awesome. Yeah, so that example's in the chat, and so the big takeaway for me is, you don't have to think about this just in terms of, well, how often do I go to the shelf and grab a denoising autoencoder? The idea of denoising autoencoders is, I'm just going to swag, is probably over 80% of state-of-the-art AI models, when you look at it more closely, are some form of denoising autoencoder. So this concept is super, super important in AI, no matter what you're doing, whether it's tabular, whether it's text, whether it's images. Yeah. Can you pass this all the way to the back row, please?
Yeah, thanks. So for the autoregressive mask that you were just mentioning, when you say like you have 4,000 tokens and you only use 10 to predict the next 3,990, but then like you probably get like 3,999 samples out of those 4,000 tokens. So like another sample would like have like the first 100 tokens filled, and another sample would have only the first 10 filled. Wouldn't there be kind of some like leakage of information because like your model knows the like next couple tokens from another sample?
That's a great question. So leakage would potentially be a problem, and the way the architecture of the layers works, the autoregressive mask actually prevents leakage. So in the 9th token position, when it's trying to predict the 10th token, none of the layers can see any information from tokens 10, 11, 12, or beyond. And for efficiency purposes, we don't do it this way, but it is absolutely equivalent to if you went sequentially and you just passed in the first token and you said predict token 2. And the other data didn't even exist, okay? And then you cleared everything and you said, now I'm going to give you 2 tokens and I want you to predict token 3. And then you clear everything and you say, I'm going to give you 3 tokens, now predict token 4. Mathematically, what we do with this mask is completely to the last bit identical when we do it all in parallel with the mask versus if we just did it in 4,000 separate predictions. Okay, that's the purpose of it. So it might take a little bit of wrapping your head around that mathematical equivalence, but ultimately that is the idea then for why I'm claiming this is a masked, a denoising autoencoder, because in the first sequence, I'm masking out 3,999 and I'm only showing you the first one and you're predicting token 2.
But that means like you couldn't shuffle your samples because then in theory, the model has already seen the solution to another sample before. I could memorize it.
Yes, and in fact, in NLP, so you can keep that back there. I put a second mic in the front. In NLP, it is fairly common to train on your text approximately only 1 epoch. Whereas in computer vision, it's very common to do hundreds, thousands of epochs because we noise the data. So we do augmentations, we do the rotations and the crops and all of this. so that's not seeing the exact same input over again. You're exactly right. People have seen sometimes catastrophic drops in performance if you do multiple epochs on your text data, because there's no really good agreed upon augmentations for text data. You can swap the word large for big, but it's not always going to be appropriate. So, you know, if there's the expression big data, and then all of a sudden you say large data, that's not quite right. You know, you can't say Big Bear Mountain is Large Bear Mountain, right? So some of these things will work some of the time, but it's difficult to have a really good augmentation scheme. And so it's not exactly, but your Gemini, ChatGPT, Quens, for the most part, they're training on text approximately.
So I was just wondering, there is this concept of sparse attention. I believe it's in DeepSeek, I think, I'm not sure, to reduce the time complexity somewhat, no, I mean, by a fraction. Can you comment on that? What is their experience in terms of accuracy? Would they compromise too much on it by doing this sparse attention?
I'd love to talk to you about DeepSeek sparse attention. I'm going to actually say, let's take that offline and chat afterwards. Okay. Yeah. So the next thing we have here is sparse autoencoders. And the idea here is, rather than physically saying, oh, I'm only going to have 30 neurons in the middle and that will squeeze it, I can have something like an L1 loss that encourages sparsity so that I wind up with the equivalent of only 30 neurons activating at any point in time. There's actually a bunch of mechanistic interpretability research right now that's using sparse autoencoders to understand what's going on, but as an actual building block in real models, I don't think I've seen this. So just like that stepwise training, I don't think this is a super important concept for people to learn. The next section, though, is a very important concept. The book does not go into the math in great detail. I'm not going to go into the math if people have some questions, but it's variational autoencoders. And so variational autoencoders are very, very, very different from the autoencoders we've been talking about up till now. Up till now, all of the models we've talked about, if you give it a certain input, you're going to get a certain output of the encoder. Okay. If you have ChatGPT and you put in a certain prompt, then you're going to get the exact same floating point values coming out of the top every single time. Now, ChatGPT does sampling. It doesn't always pick the most likely word. So that's why you actually get different answers. Okay. But the actual probabilities for all the different words are going to be identical every single time. Okay. Let's not talk about like GPUs have floating point rounding errors or whatever. That's a completely separate thing. But if you had infinite precision math, you would get the exact same answer every time. What variational autoencoders do is fundamentally different in that instead of embedding this cat image into this vector of 30 floating point numbers, it says, I'm going to give you an output probability distribution that has a center, the mean, and a certain distribution around that. And what we do is we pick what kinds of distributions we want for convenience. So almost always what you're going to see is a Gaussian distribution, because Gaussians have really nice properties and we have ways of calculating things very fast and yada, yada, yada. So they're just like super convenient. Okay. And so with a Gaussian, you really kind of only need, I'm going to say two. I'm going to be a little loose with my terminology. You just need to know the mean and you need to know the variance. Okay. Multi-dimensional Gaussian, the variance is actually a matrix. It's not like one thing, but you just need to know the mean and the variance. And that defines it. More complex distributions, you need more things in order to exactly define that. So essentially, now what happens is you pass in a cat image, and instead of getting 30 floating point vectors, you get something that says, I have a mean value here and a distribution around that particular vector. So one of the things that's very different about this is instead of, so then when you take that and you plug it into the decoder, you don't always just use the mean. Okay. What you do is you sample something, and so you will randomly get points that are near that center vector, but not exactly that. Now, imagine that you're the decoder, okay? You don't know what the heck the encoder is doing. You just know that it's giving you it's not telling you the distribution, the mean and the standard deviation. It's just sampling a random point nearby out of that distribution, okay? So you don't know what it did. And so when you get a point, you're like, well, I don't know, like you have to kind of treat it as if it were the center, but you really just don't know. And you need to somehow reconstruct the cat image that came into the model. If this is going to work, if jointly the encoder and the decoder are going to work together as a team, then there's a certain property that we need, which is nearby embeddings in that latent space in the middle have to output similar images. Okay. If you have a vector of 30 floating point numbers and just adding 0.01 to it changes a Siamese cat to a Labrador retriever, then we're in big trouble, because when we do that sampling step in the middle, we're going to get a completely different image and we're going to get a massive loss. So what we really want is like, oh, maybe if you have a Siamese cat and you add 0.01 to all the floating point numbers, I get that same Siamese cat that's sort of lying down instead of sitting. Or maybe I get a cat that's a little bit browner than the one that you input. So what you want is, so ultimately this is how you get a very interesting latent space where things that are nearby are very similar to their inputs. It's not always the case that these nearby directions are interpretable to us as humans. There have actually been research, if you want, you can look up, there's this beta VAE where they did interpretable directions. And so then you could actually see like, oh, if I change the third floating point number, the color of the main color of the fur changes from, dark to more browns to light to white. Okay. But so this is the very special property that we have in this latent space that the VAE is building. So, so I have a note here, right? So the Bayesian inference math can get pretty complicated. Ultimately, we are training the encoder to convert the distribution, let's say it's cat and dog pictures, into a Gaussian distribution, and the decoder is going to reverse that transformation. All right. So what Bayes' rule tells us is whether or not a particular training data point is likely or unlikely under the current neural network's transformation. So what we do is, if we say this looks like a really, really unlikely thing, then we tweak the neural network and we push it. And so ultimately what we're trying to do is maximize the likelihood of the data, of the training set data. All right. And in fact, this is exactly the same thing that we do with linear regression, with most supervised learning, is we're just creating the maximum likelihood of the training data. Okay. That's in the more statistical, more technical speak. The difference here that now is, instead of merely using point estimates, we're now actually associating distributions with all of our data. So this is necessary in certain kinds of modeling. So if you've ever seen people talking about how they built neural networks to play poker, all right, it's absolutely necessary to model poker as a probability distribution. I think there's a 30% chance that my opponent has a pair. I think there's a 70% chance that he has 4 cards that are all hearts and he's going for a flush. Okay. If you don't model that, if you just to pick a point and you say the most likely thing right now is that he's going for a flush, then you completely forget the fact that he might have a pair. And then in a later round, when they bet a certain way, you only have information about this. Sorry if you guys don't know poker, but so the idea is in that kind of a world, you absolutely have to have probability distributions every step of the way. You cannot treat situations as just point estimates. It's a little bit less obvious why you would want distributions for cat and dog pictures, but nevertheless, the same principle applies. Okay. So the beauty of this is that now that you have this latent space that the encoder is embedding into, if I take a sample picture, so I take a picture of my cat, he's a tuxedo cat, all right, and I get a certain output from the encoder. What I can now do is I can sample points all around that, and I can generate new pictures of tuxedo cats in different poses, slightly different black and white coloring. And this is how I have now used the VAE to build a generative model. The decoder is a generative model. We needed the full autoencoder, the encoder and the decoder, to train these guys together. So you pass in a sample image, the encoder encodes it, you do a sample step, the decoder generates its best guess, what it might have been, and then you do a loss comparing the output image to the original image. Okay. But when you want to sample, when you want to generate, you just use the decoder. And you look at research papers, you will see there are a number of research papers where they train certain something, and then they throw the encoder away and they say, oh, we're just using the decoder for whatever it is that you're doing. So this pattern from VAEs, we see this over and over again in generative models. So here's a diagram, and you can sort of see the original images might have some very funky distribution, weird shaped thing, okay? The neural network job is to figure out how to map this distribution to our desired distribution. So let's say it's a Gaussian, so we have that represented by a nice circle here. So it figures out how to stretch, twist, pull, tug this green shape into a circle. Now we have this nice property that nearby things, notice all the blue things are near each other, the red things are near each other, the white things are near each other, okay? And so then we can sample and we can generate new samples, new images or whatever from the original distribution without having to know what this distribution is. The point of this is this green shape, we never actually really learn that. We just learn that we have a neural network that is trained to go back and forth between the funny green shape and our nice, pretty Gaussian shape. All right. Again, we didn't go into all the math, but any questions about variational autoencoders? Yeah. Is that mic working or?
Does the variational autoencoder still work with the reflected method you mentioned earlier, where the encoder is kind of a mirror image of the decoder?
Probably not. Let me think. I don't know, but I feel like tying weights, I have never seen it with a VAE. Philosophically, I can't think of a reason why you couldn't use it a little bit, but in a symmetric vanilla traditional autoencoder, you could use it in 100% of the layers where the decoder has no new weights. And I'm thinking that just couldn't ever work exactly where every single layer is. But like for images, if you have some CNN layers, early layers in the encoder, you could certainly have those tied and have transpose convolutional layers in the decoder that are outputting things. So that's an interesting question. I don't know the answer. I don't know if anybody else can comment on that. Just check the chat. Okay, so there's a question online about semantic interpolation. So I didn't have this in my notes, but it's in the book. So one of the things is, if you have this nice property that in our latent space in the middle, in this, what's in this diagram is the yellow circle, if similar things in our original space are located nearby in our latent space, then you also largely, not always perfectly, have the property that if you sort of travel around in the latent space, if you just sort of drive around in it, okay, that the path you take inside the latent space is semantically, what's the word I'm looking for? Relatable to in the original space. Okay. And so what this means in more precise terms, not theoretical terms, is if I have a picture of my cat sitting and I have a picture of my cat lying down, and I embed both of those, and I have those two embeddings in the latent space of this VAE, okay, then what I can do is I can take those two embeddings, and let's say one of them is 1, 2, 3, 4, 5, 6, and the other embedding is 10, 11, 12, 13, 14. I can take all the embeddings that are just in between those two. So I can take the halfway point, the quarter way point, the 3/4 point, and I can generate images from all of those. If we didn't have this nice property of our latent space, I would get a bunch of images, but they'd be just kind of random images. Instead, because we have this nice property of similarity in our latent space, oftentimes with most VAEs, you will get something where you will see images that are in between sitting and lying down just gradually. And so essentially you can use this technique to morph images from one to the other. So that's a rather small transition, sitting to lying down. I can now take something extreme. I can take the embedding of an image that's a Siamese cat and the embedding of an image that's a Labrador retriever. And I can say, what is the halfway point between a Siamese and a Labrador? And if you did this in pixel space, what you would see is like a blurry, fuzzy thing. Okay. But if you do this in latent space and you generate an image, you're like, wow, that's kind of a Siamese colored dog with, Siamese cat eyes, but otherwise the dog shaped face or whatever. And you're like, that's a reasonable interpretation of what's something that's halfway between a Siamese and Labrador. And so you can also take, the quarter way point, the eighth way point, and whatnot, and you can morph a Siamese cat into a Labrador retriever. And so that's this semantic interpolation that they talk about in the book. Did I successfully answer that question?
If you're doing this kind of interpolation and you hold like most of the weights constant, but like only change like one weight and try to find like the in-between point, that would like kind of tell you like what that specific like I don't know how to describe it, but like it sounds more like all of the weights together kind of give you the interpolation and not necessarily like a single weight would give you like a clean.
That's right. So if I had my cat 1, 2, 3, 5, 6 and my dog 10, 11, 12, 13, 14, and I said, I'm just going to change the first one. So I'm going to go 1, 2, 3, 5, 6, 2, 2, 3, 4, 5, 6, 3, 2, 3, until I get to 10, 2, 3, 4, 5, 6. If the latent space was completely human interpretable, you'd be like, holy cow, I now have a Siamese cat with a Labrador head, but everything else about the Siamese cat is exactly the same. The first floating point number just controls the head. And if I change just the second number, then just the tail would change. And if I change just the third number, whatever, like, right? So actually, that's what they did in this beta VAE paper, is they managed to get it so that you could do that. Most VAEs, it's uninterpretable. And if you change just the first number, not only is it not going to work, I think you might even get junk that's not even a cat or a dog because it's not on the line between.
Yeah, got it. That's really interesting.
Yeah. So I have this art project idea that I just have been too lazy and haven't actually done, but people do linear interpolation between these 2 points, right? And so I thought about, well, what if you purposefully don't do linear interpolation? So what if, like, I have a Siamese cat and I have a Labrador and I have a third point that's like a dragon, and so what if I interpolate on a curve where I go from cat to dog, but via dragon in the middle? Okay. And then if you can imagine doing that, it's more or less the same thing as just going from cat to dragon and then from dragon to dog or whatever, right? But what if I then complete that circle? What is on the other side opposite from dragon? I don't even know. But so, it's interesting. Do you just get like noise, garbage pictures? Or do you suddenly somehow find that, like, well, that's weird. Like, leather couch is the opposite direction from dragon. And so if I went in a circle, it goes cat to dragon to dog to couch back to cat. I don't know. So I've had the idea that you can play around with these interpolations, and you can do linear interpolation, you can do spherical interpolation. And so then my idea is, if you just figure out different funky traces, can you get some sort of like weird patterns? What if you follow a sine curve between cat and dog instead of following a straight line, stuff like that. And again, it depends on the latent space. It's entirely possible some of these experiments, you'll wind up with some really terrible images that are just kind of garbagey.
Yeah. Got an extra question with that question I asked.
Yeah, go ahead.
So for interpolation, you gave the example. If you have the cat is 1, 2, 3, 4, and the Labrador Retriever is 10, 11, 12, do you have to have the same number, or can you just have cat 1, 2, 3, 4 and Labrador Retriever 1 and still work with that? Or does the same kind of like data points have to be there? So in the picture that you have there, there's so many blues, so many reds, and so many whites. If you want to change that and you only had maybe the same number of blues, the same number of reds, but only 1 or 2 whites, would you still be able to do interpolation, or does it have to be the same number to perform that act?
Yeah, so the number of samples you have is not critical. Okay. And I think here you can actually see there's probably slightly more blues than there are other ones. You're going to need enough that you have, some diversity of examples for it to learn from. Okay. But ultimately, though, these will be the same size vectors. So at one point we were talking about having a 30-dimensional coding in the middle. And so everything, whether it's a cat, a dog, or a whatnot, is still going to be a vector of 30 floating point numbers. Does that answer your question?
Yes. Oh, sorry. Because it goes into what we're going to be talking about next with GANs, but I wanted to kind of get an idea of this because there's a lot of images out there, like you said, are crap. And I'm guessing it's using this approach of interpolation, taking 2 images and merging them together to try to get this image like of a hand. And they like take hand of one person, another hand, another person, but it doesn't get it right. So that's why you have 6 fingers and no thumb or something like that, because it's not exactly 1 to 1, I'm guessing.
Yeah. So if we built the ultimate perfect VAE, okay, and I don't know what red, white, and blue are, cats, dogs, and dragons, okay, then everything in this yellow space would be a valid cat, a valid dog, or a valid dragon. But these are not perfect models, okay, right? There's some amount of error in them. And so if you can see my mouse, this corner here where there's no blue or red dot nearby, if we use that and sampled from it, we might not get a cat or a dog or a dragon. We might get something that just has weird colored patches and looks staticky and doesn't even look like any kind of animal at all. Or to your point, we might get something weird a three-legged, two-headed, scaly blob, you know. So yes, if this were an absolute perfect VAE that knew everything about everything and did it perfectly, then no matter what you sampled, you'd get a valid image. But the reality is you train this on, you know, a few hundred dog, cat, and dragon images, and you will have a lot of room in the latent space to have just complete garbage. All right. So looking at the time, I'm gonna need to pick up the pace. I'm gonna move on. So if you guys aren't familiar, Lillian Wang has some wonderful blog posts, including one on VAEs. And so this is a great one, and it also talks about the beta VAE where you actually have these human interpretable directions. So I'll share the link to my notes. I forgot to do that before we started. So can I get back to my notes here? All right. So here you can see in the book, they built a VAE for our fashion MNIST, and they generated some pretty decent images. This was a fairly small model. You'll notice that these images are kind of blurry. With a bigger model, you would get better images, but ultimately, the biggest weakness for VAEs was that they would generate blurry images. And a lot of this has to do, the technical detail is you use mean squared error loss for the reconstruction from the original to the final. And in optimizing that, like let's say you have some grass, what ends up happening is instead of just committing to individual blades of grass, it's like, let me just do an intermediate average green and I'll get the lowest loss. And so that's why things tend to just look blurry. There are ways to fix that, but I'm not going to get into that for the purpose of today's chapter.
I think you have a question online.
Oh, I might have missed in the chat. Oh, for denoising, how effective is it? I don't know. I don't know if I'm qualified to really answer that. Ryan, I don't know if you have a comment either.
There's a lot of different techniques that people use for like messy signals, and deep learning in general is good at handling it just natively. If you have enough data, then it can learn the signal out of the noise pretty well. So you might not even necessarily need like a denoising specific network. It might be if you have enough data, it can just already learn the patterns and figure it out.
So like, for example, ChatGPT, the researchers don't explicitly train it on misspellings. It's seen a bunch of misspellings when you scrape the internet, but even if you have a new misspelling that it's never seen before, it has learned the patterns for misspellings and things like that. So nowadays, anytime you're using one of these models, you know, I notice that all the time. I'll do like a Google search and I'll accidentally make a typo, and it pretty much always ends up giving me what I actually wanted, even though I spelled it wrong.
Richard, you have a hand raised. You have a question?
Why am I not seeing the hand raise? Oh, okay. Yeah. Go ahead.
Oh, sorry, Ted. I just wanted to. Sorry, this is actually backing up a comment or two, but I just wanted to know if, to your knowledge, is there an industry standard for accuracies in this kind of decoding and encoding? In other words, does somebody do commercial LLMs and large and various kinds of models say we've got to hit this accuracy consistently, or we don't have a final product here?
Yeah, that's a cool question. I don't think I have a long answer I can give you, but I will emphasize a certain fundamental points to modeling. Oftentimes, the loss function you're using for training your model is not going to be identical to the actual business end result use case. So in the example of images, mean squared error is usually how people calculate reconstruction loss. So you just say, I have the RGB values for the pixel in the upper left corner, and I'm going to subtract my prediction from the actual, square that sum, and that's a number. Okay. That ends up being one of the best signals for training the model and getting the model to train quickly. However, if your goal is to build a model that generates like face pictures, like celebrity pictures, what we care about is not actually mean squared error. What we care about is we want a realistic looking face. So we don't want it to be blurry. And there's certain other things like you might object if half the time it generates people where the right eye and the left eye are different colors. Okay. So this is true in almost all modeling problems. You have to ultimately look at your business objective. So what you will see, for example, in a lot of image papers is that they train the model with something like mean squared error, but they use maybe a different metric like FID in order to decide which is the best. So this is a similar thing where you have to ultimately look at your business case and say, what are the kinds of things that I can afford to have, and what are the things I can't? In image generation, one of the things that people learn, just again, to solve the blurry problem, is they figured out a way to get the model to commit on certain fine details. Because at the end of the day, when you're generating an image, you don't care whether the blades of grass are identical to the ones that were in your source image. Most people are never going to notice. What you care about, though, is that there's grass where the grass should be and there isn't grass where there shouldn't be, and that the grass, if you look at it up close, looks realistic. So in that sense, what they are doing is they're prioritizing the pattern, the texture of the grass over the pixel accuracy. Okay. And this extends to sort of all domains. You have to ultimately realize what is the thing that gives me the biggest bang for my buck for what I want. So I don't have a specific good answer for you.
No, it's I think it's a great question. We could probably have an entire session of discussion just about accuracy or inaccuracy tolerance in AI and large language models. But I mean, I would think it varies by industry, right? If you're like a large, house building firm and you're trying to create interesting images of like interior spaces or color patterns for potential house buyers, then you're going to have a kind of high tolerance for accuracy, right? If you're somebody in the FAA and you're running you're running some kind of system that helps monitor and track traffic patterns, air traffic patterns, and what airlines do, you're going to have a very, very low tolerance, like 99 point, you'll want like 99.9% accuracy, right? And so I think the algorithm that you choose in these sorts of cases for image accuracy and classification is going to be based on how much risk tolerance you have.
Yep, that's a great point. We have a problem today that these LLMs are trained on the accuracy of next token prediction. So cross entropy or perplexity, depending on how people talk about it. And it's very important that people, when they're building new models and they're tweaking things, that they ultimately measure it on downstream benchmarks. How does it do on coding? How does it do on question answering? How does it do on summarization? Because it turns out that this is the metric we use for training it, but that's not actually a perfect mapping for which models do better in the real world. So
and that kind of implies that before you do your training, you ought to have your risk metric in place. You have to understand what that would be one of the key metrics that you would do your training based on is how high the accuracy of the algorithm is.
Right. And one could argue, I'm going to sort of wrap up here and move on to the next topic, but one could argue that even as advanced models as we have today, people do not have that mapping. So people just sort of like, oh, here's the next ChatGPT 5.3. I'll test it on a bunch of benchmarks, and I'll use feels to decide. It's like, oh, it didn't do as well on this math thing, but oh wow, it did really great on these other things. So yeah, let's go ahead and release it. It's not like they have a very fixed rubric going in. Okay. Time. We're gonna have to see how we do this. Okay, so GANs are not as popular as they were. So at one point, GANs came out and they generated better images than VAEs. And GANs were very good at generating sharp, crisp images, unlike the blurry stuff we got from VAEs. So around 2020 was the peak popularity of GANs. And since then, it's been replaced by diffusion models and it's faded. So you still will see some people talking about using GANs to generate synthetic data for a particular task. People use it for tabular data, people use it for other things. So it's kind of good to know GANs. But again, the point of this is less so about the individual model, standalone model, and more about the technology. So I'm going to go a little faster here. I apologize. The key thing here in GANs is you have two models. You have the generator and you have the discriminator. And the generator is trying to generate images from the training set. The discriminator is shown real images from the training set and generated images from the generator, which we will call fake. And it's trying to decide which ones are real images from the training set and which ones are fake. And the two of them are working adversarially. The generator is trying to fool the discriminator. The discriminator is trying to prove the generator to be sucky at generating realistic images. In this case, I'm going to use images, but it can be any kind of data. So there's a quote from the book, and I've seen this elsewhere. It took me a while before I realized this, but if you see the way this diagram flows, okay, real images half of the time go into the discriminator, and the generator never actually sees a real image. Never, ever, ever, ever. The training alternates between make the discriminator a little bit smarter so it can tell the difference. And once it's really good at telling the difference, then train the generator and make it a little bit smarter. Okay. But the quote is, the generator never actually sees any real images, yet it gradually learns to produce convincing fake images. All it gets is the gradients flowing back through the discriminator. Fortunately, the better the discriminator gets, the more information about the real images is contained in these secondhand gradients, so the generator can make significant progress. So I have a note here that the gradients that flow into the generator are coming through each pixel. Okay, so it is a very dense piece of information, but I agree with some comments that I've seen in other books where if you had shown me this idea before GANs actually existed and somebody got it to work, I probably would have said this sounds like a dumb idea. And even if you could get it to work, we should probably tweak it because there's probably a better way to do it that would work better than it does. It's very unintuitive that the generator never, ever, ever, ever sees a single example from your training set. So I find it quite remarkable that it works. The thing that is groundbreaking, other than just this particular design, is the idea of adversarial learning. That lesson, adversarial learning, has persisted, and many, many models today use some form of adversarial loss, adversarial learning. So even if you don't see GANs today, it's entirely possible that when you're reading about the latest AlphaFold model, that somewhere in there, in a subcomponent, there is this adversarial loss. It turns out that a common thing that people did to fix the blurry image problem is they would add a little discriminator that just not looked at the whole image, but just looked at a small patch and says, does this patch look real? And so that was how they solved that problem, because now you can say, oh, that looks like real grass. I don't know if that's the same grass that you had in your input image, but it's no longer a blurry mess. It looks like real grass. Okay. So it's this adversarial learning that has been a major contribution. So I think Ian Goodfellow and the team will have whatever a long lasting in the history of AI for this particular contribution, even if we stop using actual GANs, because this adversarial learning is something that's going to stick around. All right, so we're going to get to diffusion models next. I have one more link here. It's GAN Lab. And if you want, this is a small GAN. This is not one that actually does images, but you can actually play around and you can sort of see the details here of the discriminator and generator sort of competing and learning. All right. GANs were notorious. They were much harder to train than, say, other autoencoders or other deep learning models that we've done. And one of the big problems was mode collapse. The book talks about it. So in fashion MNIST, if the generator ends up fooling the discriminator really well on shoes, then it might learn to just output only shoes because it's doing well on shoes. Eventually, the discriminator might catch up, and then it's like, oh, shoot, I got to switch to handbags now. But that's not what you want. You want it to learn to produce all 10 classes and to produce something general. There's even worse problems where certain generative models, they can just do something simple like output all zeros, and they can have a very low mean squared error loss by doing tricks like this. So again, this idea of adversarial loss is like one important thing, and then another thing is mode collapse, which we see in GANs, is a problem that we see in other generative models as well. Let me check the chat real quick. Yeah, I'll link the notes so you can access all the different links that I have here. Sorry, just trying to move a little bit faster here. So a natural thing you might do if you want to generate images is say, I'm going to use convolutional layers in my GAN. And it turns out that GANs are so finicky that it took people a while to figure out how to get it to work. You had to really tweak like normalizations and activation functions and a whole bunch of stuff. But eventually people did get it to work. And then famously, there are two models. The progressive GAN that came out of NVIDIA had this idea that rather than generating the whole image, let me generate something really small, like maybe a 4x4, 16 pixel. I don't know if you call it an image or not, but the idea is this would have the coarse features. So maybe the top 4 pixels in the top row would be blue because your image has blue sky, and the bottom 4 would be green, or not necessarily green like literally in the color, but they would contain information that says the eventual pixels here will be green, okay? And then you expand this to an 8x8 and you start getting more details. And then eventually you get enough details where it's like there's a dog and you can tell the dog is standing and facing to the left, and the dog is light brown in color. And then eventually you get more and more details until finally you're filling in like all of the actual pixels. This progressive GAN worked a lot better and was a little bit less finicky than other GANs. And then they improved on it. And so the most famous GAN is the NVIDIA Style GAN, and there was Style GAN 2, and I don't know how many successors to it. But what's cool about this is that I'm not going to have time to go into all the details. There's a different way that they dealt with randomization. So you can see this noise comes in at different points, and that ended up being very advantageous because, again, you don't really care where the exact blades of grass are. So you can just have this noise that comes in. You can have a signal that comes in and says, put grass here. And then you can have some noise that says, this is what the actual grass looks like. And every time you generate an image, the grass looks a little bit different. And you don't really care as long as the instructions put grass here have been followed. But StyleGAN allowed you to do things like literally have a slider that says what color are the eyes, how big is the nose, Is the person wearing glasses? Yes or no? And very, very cool for producing not just realistic images, but images where you could actually pick, do I want male, female? What color hair do I want? Do I want the person to have a beard or not? Yada, yada, yada. All right. So I'm going to move on to talk about diffusion models. Going to have to do this fairly quickly. Won't get as much into the math and some of the stuff that the book covers, but want to cover the concept here. Okay. So if you add Gaussian noise in what we call the forward progress, eventually the noise will drown out your original signal. So you start with a picture of this cat and you keep adding Gaussian noise, then eventually it'll drown out the original signal and you'll be left with nothing but noise. And if you know your math, then you can say that this noise is actually going to be Gaussian in its distribution. What we want to do is to train a neural network to reverse this process. And this is the part that's kind of remarkable about diffusion models, because it's not clear how you reverse this process, okay? So if you are towards the left in this diagram and you have an image that's closer to the full image, you could see how you could guess what the image would be without the noise. But when you're further to the right and you're closer to full noise, how can you possibly know exactly what this cat was supposed to look like? Okay. Book doesn't really talk about this. I think this is one of the key things to understand about both LLMs and diffusion models, is that there's actually an advantage to being a process with multiple steps versus doing it all in one fell swoop. Okay. If an LLM is given a math problem, I was just looking, one of the papers talked about this math problem. It was, I'm not going to remember the numbers, but it was something like 5 plus parentheses, 3 plus 4 close parent. Okay. So the prompt is, what is the value, for this expression? 5 plus parentheses, 3 plus 4. All right. And so you and I know order of operations. What you should do is you should add the 3 plus 4 and get 7, and then 7 times 5 is 35. Okay. And a mistake would be to just do it left to right. So if you said 5 times 3 is 15 plus 4 is 19, that would get you the wrong answer. Okay. But there's this in between thing where the LLM, if it's outputting one token at a time, okay, and it outputs 5, it doesn't have to say plus 3 next. It could realize, oh, shoot, I was thinking I was going to say 5 plus 3, but that's actually a bad idea. And so it could just say something like 5 is going to get added to the sum of the next two numbers, and then correct itself and then say 3 plus 4 equals 7 and 5 plus 7 equals 5 times 7 equals 35, right? So just because you committed to 5 doesn't mean you committed to what you're going to do with that 5. Okay. By the same token, when you're doing the reverse process, if you start taking away some of this noise and you think that there's going to be, I don't know, an orange pixel, somewhere over here in the center of the image, you don't have to then, you might originally be thinking, I'm going to create a cat with orange fur. Okay. But maybe in fact, what ends up happening is that orange pixel is where the ear of the cat is, or that orange pixel is where the nose is, or something like that. Okay. So, because it is this sequential process, you can fix earlier mistakes by sort of changing course. And even though you were originally thinking you were going to go a certain direction, you can actually sort of complete the process, not exactly the way you were originally going. So I think that's one of the key things to understand. My intuition around diffusion models is that in the reverse process, in the early stages, it's not that the model knows exactly what it should be doing. Okay. The model is pushing the image away from noise towards a cat image but it doesn't know exactly what's going to happen. And it's up to the later steps to sort of correct if there's any sort of mistakes. All right. When you're driving, you might steer a little bit further to the right than you really should have. And you're not committed to forever following that path that you originally decided. You can decide later on, I'm going to steer a little more to the left than where I originally thought. And that's my intuition around how these diffusion models work, is that the reverse process lays a foundation, and if necessary, later on steps will correct that a little bit and guide it ultimately into a final image. And so even if you made like a terrible mistake, like to the best of my knowledge, there are no bright red cats, and you have this red pixel right smack dab in the middle, you can decide, oh, my cat's going to be wearing a red collar. That's how I'm going to solve this mistake that I made early on. All right. So I hope that makes sense in terms of there is no neural network that can completely take noise and turn it directly into a cat image. And that's why we don't have a diffusion model that in one step just goes from all noise to. They're always iterative because it's doing this process of laying a foundation and then potentially, if necessary, doing some small mid-course corrections. Okay, so one thing that I want to add, and I apologize, I know we're over time here, in terms of intuition around diffusion models. So there's later work that showed the connection between the score function and this diffusion process. And what the score function is related to is the gradient of the data distribution. Okay, technically there's a log in there, that's just a scaling factor. But so it's a little bit hard to imagine this in like image high dimensionality, but if you imagine like a much lower dimensionality thing, like a distribution, a 1 or a 2D distribution, okay, you have points that are realistic samples. These are your realistic images. And then you have points that are like, this is not a realistic image. It's very staticky, or like, for example, the grass is very blurry, okay? And so the gradient is the direction that points from low likelihood to high likelihood images. And so as the reverse process is denoising images, what it's doing is it's actually walking along these gradients from the low likelihood images to images that are high likelihood, just like the distribution in your training set. And so Yang Song is famous for making this connection and saying that what the model's really doing is, the neural network is doing is it's learning this gradient. And so when it's denoising, what it's doing is walking uphill towards likely images. And there's some things that you need to do in order to get this to work. And he did some stuff with stochastic differential equations, and he figured out there's an equivalence with ordinary differential equations. And when you are generating images with one of these diffusion image generators, it's using an ordinary differential equation solver, an ODE solver, to basically say, if I have this differential equation, that's the path from low to high probability images, and I'm here, then where would I be if I followed this path for a while? Okay. And ultimately, the thing that people have been trying to do is to say, how can I make diffusion models faster and faster and faster and require fewer steps? The book, I think, mentions a model that required 4,000 steps. Okay. People are like, no, I want to do it in less than 5 steps. That's really, really not easy. Okay. So if you want to know the latest in image generation, now what we have are these flow matching models. And the thing that people realized is diffusion is a thing in physics that people understood. Brownian motion, you put a drop of colored dye in a clear water and you can watch the color disperse, okay? And it gives us a process that we can model where you go from some well-defined known distribution to this full Gaussian noise distribution. But it turns out that's not the only way you can get from your known distribution to from your data distribution to a known distribution. Gaussian noise is one way, but it's not the only way. And so the key insight is that these gradients that the model is learning to follow, the score function that diffusion models are learning, they're following curved trajectories. And so the more windy that curve is and the tighter the curves it has, the harder it is to take big steps and predict where you're going to be far in the future. Okay. It would be really nice if the path was much straighter. Then you could actually take much bigger jumps instead of having to take small steps following this windy curve. All right. And that's what these flow matching models do, is they don't use Gaussian noise. They use a very different kind of noise schedule. And in fact, in the gory details, you don't even have to know exactly what the noise schedule is. You just have to know that you want your path to be as straight as possible. And so as far as I know, that's pretty much the latest in research today, is these diffusion models. You're able to build very large neural networks and generate images that are more accurate than GANs. That was one of the questions. I'm sorry, I don't have a whole lot of detail to back it up. But all the image generators these days are not using GANs, they're using this diffusion type process. And the cutting edge is using flow matching, which is still the same idea that you're noising an image in the forward direction and you're denoising it in the reverse direction. We're just not going to use Gaussian noise now. We're going to use a different mathematical formulation that gives us straighter lines. And in the original formulation, maybe it's 4,000 steps, but we can get a very close approximation in perhaps 5 steps, 3 steps, 2 steps, and we can get much faster image generation than if we did the diffusion way, where because it's curvy, in order to stay on the curve, we need to do much smaller time steps. So again, if you were driving on a windy road and I was, blocking your vision, if it's a windy road, you would want to be able to see fairly often, like, every half second or something like that. But if you're on a perfectly straight road, then you might be able to get away with only looking once every 3 seconds, every 5 seconds. And that's the same general idea here. All right, I got a bunch of links. My last comment on diffusion is now another hot area of interest is, can we build text models using diffusion? So there's a lot of research in diffusion LLMs. I think one of the key papers to look for this is the LADA paper, large language diffusion models. Here, there's this fundamental difference because our vocabularies are discrete distributions. They're not continuous. You cannot just add infinitesimally small noise to the word large. So things don't work quite as well. The success lately seems to have been with masked models. So we're kind of getting a little bit back to this denoising autoencoder business. But so in the LADA paper, they mask out tokens, and the model, it starts, they mask out more and more until you end up with just all mask, all noise. Okay. And the reverse process is you start filling in words, you start unmasking them. So it's a very simple idea, but it's hard to get it to work well. And ultimately, they have to do things like I talk about correcting mistakes from earlier decisions. It turns out it works better if you let it sometimes remask a word that it already unmasked. If you don't let it do that, then it's committed. It's, you have the word large, it's just stuck with it. But if you start filling in the words around it and you're like, I really don't like large there anymore, then you can just remask it and then repick a new word. Okay. And so that's where there's a lot of active research. I don't know. I know Inception Labs, has a coding LLM. We could talk a little bit. It turns out that for whatever reason, coding is an easier task than general chat. I'm not really sure. I have to think about that. But so they have a coding diffusion model LLM, and other people looking at it. But right now, I'm not aware any of the models that you use out there, Kimi, Quen, GLM, they're still all GPT style autoregressive LLMs. But there's a lot of research to see, because diffusion can do things in parallel and can potentially generate the text faster than an autoregressive LLM. So that would be the win, is can we generate text 5 times faster with a diffusion model? They're not quite there yet in terms of quality, but interesting research, and they're getting close. All right. Any final questions? I apologize. I know that I kind of really sped things up at the end, towards the end there. All right, let me paste the link in the chat. I'll also put it on Slack. All right. Awesome. Thanks, everybody. Appreciate you coming out. And for those of you who are able to, thanks for staying late. Programming note, quick note. We are not going to have a meetup next week due to some scheduling conflicts. And then in 2 weeks, we'll announce it. We're finalizing the topic. All right. Thanks, everyone.